Hello viewers, in this video I will discuss about electric field lines. So in earlier lectures we have discussed about electric field. Okay, so first I will represent the electric field due to a positive charge Q. Okay, so you know that for this particular positive charge the electric field will be in radial outward directions. So it will be in the radial outward direction. Like this only we have represented the electric field in our earlier lectures. Okay, so now I will represent this diagram in a different manner. Okay, see, so I have a positive charge here. Okay, okay, fine. So I have represented the electric field lines. See the difference. So this is the view of your electric field lines. Okay, so see the electric lines are represented with arrow marks, and you also see that the length of the arrow marks are different when you go along the distance. Okay, so here this arrow mark are very long when you place near the charge Q. Okay, so nearby the charge we see that the length of the arrow mark is very long. It represents the strength of the electric field. So it represents that the nearby to the charge the strength of the electric field is very high or more. So as you go distance, because you know that the value of electric field is inversely proportional to your distance square. Okay, so as you move away from it, we see that the length of the arrow mark reduces. That represents the reduction of your strength of the electric field. Okay, so now what is electric field lines? What it specifies? So what is electric field lines? So electric field lines is the pictorial representation of electric field, pictorial representation of electric field across a configuration of charges, so it is this a picture, this picture represents the electric field around a charge configuration. So this arrow mark indicates the direction of the electric field. Okay, so now what about the magnitude of electric field? So the magnitude of electric field or the strength of the electric field. So the magnitude or strength that is given by, so the magnitude or the strength that is given by the density of the field lines. That is given by the density of the field lines. Okay, so see, so I am going to represent the electric field lines with more dense field lines. See here, I am going to draw more number of field lines here. Okay, so from this we can see that I'm going to take a region here nearby. So I'm going to enclose the area which covers these field lines. Okay, so nearer. I'm going to take another area. You can see which covers this area away from it. So this one. Okay. So now I'm going to take another area. See here, more away from it. So it is C. So let's take this as A, this as B, and this as C. So when you compare all these areas, we see that this particular area covers more number of field lines. So it represents that this particular region has more dense field lines. More dense field lines. It represents a strong field. It represents the strong field. So when compared to A from the C, it represents. So the B is in the medium stage. Okay. With respect to C, we see that this region has as less dense of field lines. Less dense of field lines. This represents weak field. So you all know that the field lines nearer to the charge are more dense. So as we move the distance away from the charge, we see that the density decreases due to more spacing of the field lines. So it represents a weak field. Okay, so nearer to the charge we have a strong field. When you move a distance away from the charge, we see that we have a weak field. Okay, so this is the representation. So this is about the density of the field lines, which represents the magnitude or the strength. So this is about electric field lines. So now we will discuss some more points regarding electric field lines. Some more points, some important points regarding electric field lines. So now I am going to discuss some important points. Some important points about electric field lines. So see that field lines field lines means electric field lines start from positive charge, and end at negative charge. So field lines start from positive charge and end at negative charge. Now see here. So here I have a positive charge and nearby we have a negative charge. So if I have an arrangement like this, positive and negative, the field line starting from positive charge always it ends at the negative charge. So field line starting from positive charge always ends at this negative charge. So starting from this positive charge always ends at this negative charge. Like this. Ends at this negative charge. So coming from this, we'll try to end like this. Okay, so I'll draw this particular diagram. Okay, similarly, if you moving like this, it will try to move like this. Okay, see that the positive charge from the positive charge will be moving radial outward direction. You all know that. So nearer to negative charge, we see that it will be ending towards the negative charges. Okay, so this will be the direction of the electric field. So always the field lines start from positive and end at negative charge. So this is the representation. Okay, so what is the second point? So second point is in a charge-free region, the electric field lines are of continuous curves without any breaks. See, without any breaks. So in a charge-free region, it means that, so here, so if I have a charge plus Q like this, so you know that electric field will be in the radially outward direction. Okay, so we see that nearby to the charge we don't have any kind of charges nearby to it. Okay, in such conditions, see in a charge free region, so nearby to this positive charge we don't have any charges. So what happens to these electric field lines? It will be moving, it will be having a continuous curve. Okay, the curve will be continuous without any breaks, because to the nearby we don't have any charges, because we know that the field line starting from positive charge always end at negative charge. So here where it ends, it does not have any charge nearby, so all the field lines will be moving in a continuous curve. Okay, this is about the second point. Okay, so with respect to this diagram, now here we have drawn this kind of a representation of electric field when we have positive and negative. So what happens when you have both like charges, that is when you have both positive or both negative? So how will you represent the electric field? Okay, so you see that the electric field lines, as both are positive charges, we see that there will be a repulsion. So the electric field lines moving in this direction will be repelled in the same direction, in the opposite direction, towards the same line of action. See, it will be repelled like this. So the electric field lines coming from this charge, like in this direction, will be repelled again. So it will be in this direction. Okay. Similarly, the remaining electric field lines, the coming from this, it will be repelled like this. The lines coming from this, it will be repelled like this. Okay. Similarly, like this, it will be repelled. Okay. Okay, I think that is enough. So all will be pointing in outward direction. See that the field lines coming in the radial outward direction like this will be just, it will be in repulsion. You have to, for repulsion it will be just bent like this. Moving, it will be bent like this. Okay, like this bending. Okay, see, due to repulsion it will be bending like this. Okay, so this is the arrangement of electric field lines when we have both positive charges nearby. So it will be the same when we have both negative charges also, but the direction of the lines will be in inverse. Okay, this is the representation of the electric field lines. Okay, fine. So I will have this one. Okay, so now the third point. Tangent to the electric field lines. The tangent to the electric field lines represents the direction of the electric field. Represents the direction of the electric field. Okay, so see here, if I am drawing a tangent to this particular electric field line, see, at this point this will be the direction of the tangent. So at this point this will be the direction of the tangent line. At this point this represents the direction at this point. So here, so see that the tangent, this represents the direction of this electric field line. Okay, so I'm doing the same here also for this particular point. See, at this point this will be the tangent, at this point this will be the tangent, at this point this will be the tangent, at this point this will be tangent. So see, this tangent represents the direction of the electric field lines. Okay, so this is about the third point. Okay, so now we'll move on to the fourth point. So I'll have this. So here I represent the fourth point. So what is the fourth point? Field lines, that is electric field lines. Field lines, we can write, cannot intersect each other. Field lines cannot intersect or do not intersect each other. Right, field lines do not intersect each other. Okay, so if such a case, if such condition happens, See that if we have two field lines intersecting each other, now you see that the tangent represents the direction of the electric field. So for this particular line, this will be the tangent. Okay, maybe this direction or that direction. For this particular line, this will be the tangent. Okay, if it is A and B, see, for A this is the tangent, for B this is the tangent. Okay, so but you know that for electric field lines will be the direction will be unique. So in case of electric field lines, the directions will be unique. You have only one direction, but this line says that it represents two directions of electric field, because we have the tangent, they are pointing in opposite directions for the two curves A and B. Normally for all the curves we see that the tangent will be pointing in only one direction, but here we see the tangents are pointing in opposite directions, so which is not possible. Okay, so which is impossible. Okay, so it represents that field lines do not intersect each other. If they intersect, it is not possible, so they do not intersect. Okay, so this is about the fourth point. Now we move on to the fifth point. Electrostatic fields do not form the fields, electrostatic fields, they do not form closed loops. They do not form a closed loop. Okay, that is electrostatic, because that is the nature of the electric field. That is the nature of the electric field with respect to electrostatic fields. Okay, now the sixth point. Parallel lines equally spaced lines, parallel lines equally spaced lines represents the electric field, represents the electric field to be uniform. The electric field to be uniform. See, parallel and equally spaced. This represents the electric field to be uniform. Okay, this is about the sixth point. Okay, and I think I can write the seventh point here. The seventh point here. Okay, we have space. Let us see if I have space here. Yes, I can write here itself. The seventh point. Seventh point. Electric field lines are perpendicular to the surface of a conductor. Okay, so they are always perpendicular to the surface of a conductor. Okay, so this is the 7 more important points regarding electric field lines. Okay, so in this video we have discussed about electric field lines, this direction and the magnitude, and we also discussed some more points about electric field lines. Okay, thank you.